Ciao! In today's video, I want to share about an exploration using OCI technology and specifically OCI Artifact as a mean to package, sign and distribute machine learning model and their metadata using this infrastructure. These provide several interesting and composable capabilities that go from the original packaging of this machine learning model asset to actually the distribution as a ModelCar in order to be used in distributed environments such as Kubernetes with the KServe runtime environment, to as well as providing a bootc, so a bootable container that can be used in a Kubernetes environment, but for as well in a virtualized or bare metal. We are going to use this diagram for the remainder of the presentation and demo today, and we start here where I'd like to point out that when we speak about machine learning models, they are composed of two key areas. One is the model asset itself. These take the form of a single or multiple files. We can think about them as the TensorFlow format, can be serialized as well as a pickle or a joblib. It can be a specific file format for machine learning models such as Onyx, or as well a GGoof, specifically when thinking about LLM. This is the model asset itself. Then, as any model is also characterized by some metadata. Here, I like to think about this metadata as generic key value pairs, but that we could also think about persisting them in a YAML or JSON format. And then, as we have these assets, say as files, we could decide to package them as a OCI artifact. And we're going to see these now in the first step of the demo. First of all, we need some machine learning model file and create some metadata out for it. So here a very simple exercise, and it's not really important for the scope of this demo, only to understand that what we generated here is that as we see linear is our model. So if I give it the one of the test data, it will generate some prediction out of it. So here we can name this variable like the prediction given the test value number 1 and the test prediction that we want to actually realize is that it is the one coming from the test data. So if we go here and we say my predict, my test predict, we can see what we get out of it, and indeed we get that when we ask the model to predict for some values, it generates an answer here that is the same one that is coming from the test data. Right, so this is just we can think about as a machine learning model as a opaque box that given some input, it will predict some output. So this was just to quickly test that everything is working as expected for this very small machine learning model. Now that we have that, we can decide to persist it. So what I just did here is that I've persisted my model as a joblib format. So I've taken my model and I persisted it. As I indicated, this is today's date. So this is the file that I want now as my file format for the machine learning model. I also want to remind that I've taken some metadata. In this case, for the scope of this demo, I've just run the calculation of the accuracy score, and therefore this is what we are going to use as a stand-in for the machine learning model metadata. Right. So now that we have a file and their metadata, some of them may come from calculated function, or some of them might be hard-coded value. Here, for instance, is the, let's say that the author name, we want to give it a license. Here is the file, and I'm going to store it. I'm going to store it in a local OCI registry under this organization and under this name. So as I run this one, we are going to see that it has successfully pushed to this local registry. Here, what I have behind the scene is a local queue, but could be as well any other OCI compliant registry. I'm just using queue for the scope of this demo, and as a sign in, as we can see, it has generated some tag. So I have here the information, so this is the manifest. It's also, for convenience, I'm also rendering some of the metadata as annotation, but actually behind the scene, what there is here are some layers. One layer is dedicated to the file of the machine learning model itself, and other layers are dedicated to metadata and are used as manifest configuration as well, and annotation here. So this was quite pretty trivial. So what we did is that we've taken our machine learning model and the metadata and we store it in the OCI registry. So now we can go on the way back. So we have the OCI artifact representing our machine learning model in the registry, and we want to download it. So what we did with this command, in this case I'm using a generic Horace library, but you can think about this as a standing place for Docker, Podman, or any other OCI client. And I've downloaded some files in a temporary directory. So we can just briefly explore it here. This is the original file that I persisted, plus some metadata. And these are the metadata that have actually valorized coming in during the original push. Now, what I found that it's very interesting for using this OCI artifact technology is that I can get kind of creative as well with the media type that I can use for the different layer or the different files that in this case I've stored inside. And in this case, if I want from that OCI artifact reference to download just the model file, I could do so. And in this case here, I just have a placeholder, and this is what I've just saved. So just downloading the machine learning model file, possible. We can as well use this filtering mechanism to build a way to retrieve the configuration of that manifest. So what I'm doing here, if you remember, there are some metadata that are persisted both as files, as manifest configuration, and as annotation. In this case, what I just did here is that I'm using the same filtering capability of pulling only the layer of interest to actually retrieve what could be thought about as the metadata for that OCI artifact. And as that OCI artifact represents a machine learning model asset, then these are the metadata of that machine learning model asset. So ML artifact latest actually has this metadata. This is interesting because we can build on top of this infrastructure. And what we can do is that we can pre-prepare some test data in this case. So I'm pushing actually the same file, but we can think about, for the scope of this demo, being different model versions. As you can see here, I've given those different tag names, and I'm just using different accuracy value. So if we go back to the registry and I just refresh this one, we will see that they have different accuracy value here represented for simplicity's sake as an annotation, but what really changed is the manifest configuration inside of them. And since I've done so, I can reuse what I did in the previous exercise in order to crawl the manifest configuration, so the metadata of those machine learning model assets, in this case for those three versions. So I'm just saying, hey, crawl for me the result of those three. Then as we crawl the result, I can use here JQ to say, hey, give me what is the reference of those crawl result which has the max accuracy. So this is just the first step in the diagram. And what we did here is that we stored our machine learning model asset and its metadata as an OCI artifact. Being an OCI container technology, we can think about assigning it. We can think about starting to build attestation on how we build and started to distribute this OCI reference. And when the Kubernetes announcement proposal 4639 will become available, it is likely that we will be able to directly mount them inside of a pod, inside of a container, so that the container application can access the assets, in this case the files, that are contained in this OCI artifact. Since we are not there yet with this Kubernetes announcement proposal, then it means that we can use, at least for now, and actually we will see how it is a composable concept, ModelCar. Next. So we can see briefly about ModelCars, and here I'm showing the documentation of the KServe project and how to build a ModelCar. So in this demo project, what I did is just integrated the two steps together. So let's imagine that at some OCI reference, I have my OCI artifact of the machine learning models. Here I'm using a builder image. So in this phase, what I'm going to be based on, just for convenience, another ORAS container in this case, and I'm just making a pool of what is my OCI artifact that contains my model and the metadata. And what I just realized as a part of my container image for ModelCar here, I've simply copied over the model in the right directory as the documentation of the KServe ModelCar asked me to do. So here I've pre-recorded some step in order to save some time. So this is a container file that in this case hard-coded the coordinate, the reference for the OCI artifact, but of course this can become a builder argument. So of course we can compose it and make it even more reusable. So just a couple of commands in order to build the container image of the ModelCar and to push it to Quay. So in Quay, basically I've been going from this step to this step. So what I did is that I pointed to an OCI artifact for machine learning models, and I've realized a ModelCar out of it. So in our map of the territory, we just here. So we have produced this container image for the ModelCar. We can use it as a KServe, the way that is intended to be, but as well, and this is what we're going to see next, I'm going to use it for other purposes as well. I could reuse this format in order to make it as a init container to be used in bootc. And this is what we are going to see next. Right, so now we can approach the final step. So we want to go from ModelCar to bootc. We just seen that we have a bootc container image in our registry, and I want to create the bootc. The bootc image contains, in very short and layman terms, the Linux kernel, everything that I need from an operating system to run, plus as well the server runtime in this case, and the ModelCar, or the ModelCar that actually includes in itself the model that I just wanted. Here I've highlighted some of the I believe what are important characteristics, but I will just going to show it to you in the full file. So this file follows the guidelines that are provided as part of the Podman recipes. So it mimics them, but of course will be subject to making them more reusable as we will receive feedback. So I'm starting with a bootc image here for CentOS, and I'm copying the key so that eventually I could just SSH into this bootc image. And what I'm copying over for systemd are the quotelet file. The quotelet file in this case define a very simple topology that what I realize is a service in a Kubernetes style manifest file that actually can run my machine learning model and making the prediction that I want. So this is the systemd unit definition, and what it's saying is, let's say, hey, I want to run this YAML that happens to be a Kubernetes manifest as a service for systemd. And what we have here, as we will see, we have the serving runtime of the KServe project, and I'm reusing the ModelCar. Not as a sidecar container, so I'm not using the ModelCar in the original way that is intended to be shown to be used in a KServe environment, but as an init container. And I'm doing that just to showcase the power of composability and using the technology in potentially different ways. I'm not saying that this is the way that has to be used. I'm saying I'm just using this as a mean to showcase the different setups that we can use to compose this bootc image. So what the bootc image, when it started, what it will do is that it will start this kind of service, a service for making the prediction using the KServe serving runtime, using the model that I just provided earlier. And in order to make it faster, let's say that we are thinking about using this container image in some virtualized or bare metal environments, I'm already pre-caching the image, because since I'm building this image, I know the other image that are going to be needed. So the result of that, here I'm just showing the commands that I'm using to use Podman to build this bootc, and then push the bootc inside of Quay. So we can see the results here. So we went from the ModelCar to the bootc, and we wrapping the KServe runtime pieces that we needed in order to realize our services. So this is the way that we can build a bootc, and what I'm going to show you now is one way to reuse it. So we can use this bootc as in a Kubernetes cluster, but I can as well build a virtual machine image for it. So I can show it here in Podman. If I go here, I have my tab for the bootable container, and what I did is that I've taken that bootc and I just dump it as the virtual machine ISO, actually the virtual machine raw file in this case. So what I can do with that is that I can run it as a virtual machine on my system here, just to showcase one possible application of that. So to do so, I'm just going to copy over this magic incantation on the side, and what is doing here is that is starting as a virtual machine that kind of like that deployment scheme that I wanted. So what is happening here is that this virtual machine contains the service, in my case my machine learning model server, that is going to make the prediction using that machine learning model. And what I can show you here, now that that has started, I can start a terminal, and I can copy over the commands that I want, just to showcase some of the possibilities. So let's make the first try at run. So what I've been doing here is that I have that file. In this case I've used input0. Input0 is a simple JSON file that contains the format that is used by the open inference protocol used by KServe, and I'm reusing the same structure, and what is being answering here is this virtual machine server. So this is very powerful because now I can make the use it in this case transparently. I'm reusing the KServe open inference protocol, so actually I don't care too much what's behind this IP address, because the way that I've composed this service, actually I don't care if it is actually a virtual machine responding, is it a Kubernetes service, it is a bare metal server with that bootc image running. From the use case of the consumer of this service, I really don't care. So this is, I think, one of the powerful concepts that this bootc enables in this case, because we are combining the kernel, we're combining the basic of the operating system that we need, in this case of this demo, the model server from KServe, and the model, as I'm reusing the ModelCar, but it contains the model that I originally provided. And I could decide to lift and shift this bootc container image inside of a Kubernetes cluster. In that case, it wouldn't use the kernel from that container bootc, it will just reuse the pieces of information, but for me it's fully transparent. And as well, that bootc, I can just dump it in a virtual machine and run it as a virtual machine, or I could even just use it in a bootc for a bare metal server that I have somewhere that is enabled with a bootc, and just point it to that container reference. So this is really powerful, but not only because I think it can be reused in these ways, these are properties of bootc, but because, as I've tried to show here, is that the way that we are building the bootc reuses primitives that can be decomposed. For instance, given this bootc image as a kind of like if I start from the end, I can decide to just reuse this part of the system and use it in a Kubernetes cluster because I just wanted to deploy it as is. But as well, since this is a ModelCar, then I can go to a KServe enabled cluster, and then I can point KServe to this ModelCar, which is a native concept inside of a KServe. I think this really showcases a powerful integration mechanism, not only for reusing the technologies in different ways, but as well the power of composabilities. I think that it goes in the different direction. So we've been going in this demo from here from the left to the right, but we can think about use cases that may require to go, as we are modernizing some deployment strategies, going from the right to partially to the left. I think these is what I like about these technologies. We are going to move next to showcase some other integration examples. I want to show you now another integration example integrating what we've been seeing in today's video with as well Kubeflow Model Registry. So for more information about Kubeflow Model Registry, I invite you to check out the information on the website kubeflow.org. And what I'm going to have here for today's demo is that I'm using the Kubeflow Model Registry as a local Podman Compose, and we are going to integrate it with the Quay OCI registry. So in the case, so we've learned so far that we can take a model, wrap it as an OCI artifact, and then push it to an OCI registry. Let's now see how we could decide to combine the two things together. So in the first step here is nothing fancy. I'm just creating a couple of client instances, the function that I'm using as a helper to connect to OCI registries, and the model registry that you can take from Kubeflow. Now, here, for the simplicity's sake, I'm reusing the same model file that we've seen earlier, and let's say that we have, again, some metadata that we want to track about it. So we have learned that we can use the functionality that we've seen in order to push it to the OCI artifact. And so what we are going to see is that this provisional tooling that I'm doing, what it will do is that first it will push it to an OCI registry. As it is being pushed to an OCI registry, then I have a reference, in the case the SHA. And then I can use that in order to index those model and metadata on the Kubeflow model registry. Let's see that in action. So what I'm doing here is that I've successfully pushed it to the, in this case, the local queue. So let me just show it to you. What I just did. So if I log in here, I did a little push, and therefore you can see a few seconds. So this is the latest, okay? And it has, as we have learned, some metadata. In this case, the accuracy is 987, just in this case. Then finally, what we can do is that we can query the Kubeflow model registry to give me the information that you know about that version. So in this case, in the Kubeflow model registry has been indexing all the metadata that have been asked, like the name, description, the model format, and so on. So this is an information that I wanted to track. So now that I've done this part, what I can do is that I can, this is one example of integration. Now what I can do is do it also in another way. I can think that first I have in model registry some model that I've been indexing. In this case is a model, an Onyx model that I've been indexed on Kubeflow model registry, taking it by importing that from the GitHub, raw download. So in the model registry, there are the metadata and the pointer to the model that I want. So here is GitHub, but you can think that it's pointing to an S3 bucket or to your PVC or sort what is needed for your metadata and the tracking of the URI. As we're moving from the inner flow to the outer flow in order to sort of like cut the release, we can think about it. Then we wanted to say, hey, let's take the metadata that maybe we are iterated through on top of Kubeflow model registry. Let's take the model that is being pointed at that entity, at that location, and then let's wrap it, let's package together an OCI artifact, and let's push it to an OCI registry. So what I'm doing here is exactly that. So let's say that I have the name and the version that I want to cut the release for. And what I'm doing here is that I'm using Kubeflow model registry to get the information that I want for the different logical model entities of Kubeflow model registry, which are registered model, the model version, and the model artifact. This contains some metadata, and then I can push it. So let's see what happens here. So now what has done is that it has taken the model file pointed by that URI, the metadata that model registry has been indexing, that the model registry has been cataloging it, and pushing it as an OCI artifact inside of the OCI registry. So if I go back, yeah, it's here just now. And so here there's going to be the tag. This is the tag that I wanted with the information that I've used. So again, the metadata that has been indexed in model registry are here showcased as a manifest annotation, but let's not forget that those are also embedded as proper manifest layers inside of that, and the manifest configuration for this version is pointing to this metadata following the recommendation and the blueprint from the OCI specification. I think this it's a really interesting integration because it showcases to you a couple of integration showcase, in this case with Kubeflow model registry, but you can think about integrating that as well, this technology, this proof of concept, with others use case. So just to recap, what we just seen is a couple of possibilities. Let's say that we have on hand a machine learning model, a file asset, and their metadata. What we did is that using some provisional tooling, we pushed it using standard OCI compliant libraries to an OCI registry first. Why do I do that first? Because I want the SHA in order to unanimously locate that model that has been stored. And I take the metadata and I make the Kubeflow model registry point to that OCI artifact that is inside of the OCI registry. This was a first integration example. Another integration example is that I want to cut the release. So I am already in model registry with some cataloged, some indexed metadata information about the model. And what I'm doing is that I'm saying, okay, now I want to cut the release. So I'm taking the metadata, I'm taking the file, I'm building an OCI artifact out of it, and I'm pushing it to an OCI registry. After that, what happens are the same pipeline step the same workflow that I showed you earlier. We could decide that a Tecton pipeline triggers, and we go from the OCI artifact of the model to the ModelCar and then the bootc and so on. So this is one way of integrating. Now, this is a showcase as integrated inside of a local environment. In this case, I'm using Jupyter Notebook only to capture my notes of the demo at some place and the screenshot, so that if you want to check out the repository, you may try to replicate or roll your own. But this is a way to showcase that this is also possible potentially inside of a Tecton pipeline or any other pipeline and workflow or orchestration that we may need on top of Kubernetes or your local environment. So I think that this is a really interesting capabilities. What I really like about this technology is the power of composability that works in many directions, and as well the fact that these technologies is nothing kind of new. It's like this is what we've been using so far for the past years, is just showing the capability of being applied to a new an additional use case. And what this I think enables is that since we have a lot of the infrastructure already available, then we can go and distribute a machine learning model in a secure and a trusted way and integrate them with the technology that we need with the OCI containers in order to reuse them inside of Kubernetes, inside of virtual machine, and on bare metal as we need. I hope that this video was interesting. I invite you to check out the repository. I will link it down below, and please let me know your feedback. Let us know what you think about this one, and I will see you at the next video. Bye.